Now, that's the first chapter. In the first chapter, we are supposed to go with a few things, and that's pretty much the basics. For example, we are supposed to start with states of matter. Now, the states of matter are solids, liquids, and gases. These are the three states of matter we are supposed to discuss about. That's pretty much what we have on this page. Now, what's important is that we understand the structures that are usually drawn for solids. Take a look, the solids are regularly arranged in proper layers. You would see that all the particles are touching one another. So they are actually tightly packed and properly layered, which means the packing is regular and tightly packed. When it is compared with liquid, it's somewhat different. You won't see any layers. They are close, not as much closer as the solid particles were. They are not as tightly packed either, and they can move a little bit. We commonly use the phrase that they are able to move around their fixed positions or slide over one another, which actually gives the liquid the property to flow. All right. And when we talk about gas, and the same volume will consider very less number of molecules. They are far apart from one another, as you can see the distance between them, and they can move in a very random way. We always use the word for the arrangement of particles to be random in case of liquid or in case of gases. Now, they actually move at very high speeds, but they move haphazardly. The word we use is haphazard. Haphazard means that they don't care about what they are going to collide with. They might collide with one another. They might collide with the wall. They might collide with the lid of the container or whatever that is. When we discuss about this in terms of forces of attraction, there are three things we need to keep in mind. In case of solids, there are very strong forces of attraction, which actually keep them together, hence this tightly packed structure. When we talk about liquids, they have forces which are less effective than solids, but definitely more effective than gases. So the particles can move around a little bit. And when we talk about gases, they are actually moving randomly at high speeds, and that in all directions. So we say there are almost no forces of attraction. Almost. Don't forget this word. This is important. You can't just simply write no forces of attraction. That would be considered incorrect. All right. So we say almost. Almost means that in under specific set of conditions, these forces may appear to be stronger. And when we're going to move forward, we're going to say that those set of conditions contain high pressure and low temperature. High pressure means we can bring them together, and low temperature means we can slow them up so that they can develop forces for one another. This movement, which I'm discussing in terms of the regular arrangement, or solids being able to vibrate, liquids being able to move around a little bit, and gases being able to move around at high speed. Yeah, can you hear me?
Hello? Yeah, it was a bit laggy.
Yeah, it was a little lag, but now it's fine. Okay. So I was talking about the movements, and I was saying vibration
I feel
for
pretty
solids.
clear on this topic. I think we can move on to the second topic. There it gets more complicated.
Okay, sure. Let's move on. How about interconversion of the states of matter?
Yeah, I know this.
So should we keep moving on, or I need to explain a little bit?
No, unless you feel like there are like main points.
Let's just go through it quickly. We know that the solid can be converted into a liquid. The process is known as melting. It requires some heat energy, and when we take the same heat, the process is reversed. Let me tell you, this is a physical change. And the other process is known as freezing, and the points at which this occurs is melting and freezing point. For most of the materials around the planet, the freezing point and the melting point is same, but there are exceptions in which freezing or melting point can be different. Okay, so let's go to the next page because this doesn't just contain more information. When we talk about the conversion of liquids and gases, this is boiling. And again, once again, it's going to need some heat energy, or it's condensing. the other way around when we convert a gas back into a liquid. This needs the energy to be taken out, or we can simply say we cool it out. Now, we need to differentiate at this point the difference between boiling and evaporation. Remember, boiling only occurs at boiling point, a specific temperature. However, evaporation occurs at all temperatures. Remember that if we talk about pure water will boil at 100 degrees centigrade. However, it can evaporate at any temperature in between 1 to 99 degrees centigrade. So that's the difference between evaporation and boiling. Boiling occurs at a specific point, we call it boiling point. Evaporation occurs at all temperatures. What happens to the state of matter is pretty much same for both. Clear enough?
Yeah.
Okay, so moving on, let's clear this one up. Now, in case of evaporation, as he said, it's a little different. The average speed of particle varies with the temperature, but at each temperature, some particles will be moving faster than the average and others more slowly. So we can actually categorize them into three different categories. This one has the highest energy, or at least we can say that they have the highest speeds. The energy and speed can be easily linked with one another. So this one has the highest energy. The ones over here have medium energy, or we can also use the word mediocre for them. They have the medium energy. And the ones sitting at the bottom, or the ones that are not even moving much, have the slowest energy or the slowest speed. All right. So we can categorize them into three different categories. Remember, the ones who are going to evaporate are the ones with the highest energy, or the ones closer to the surface. They are going to leave the surface, and we say that they have been evaporated. Okay. It's just those particles which are closer to the surface, which don't experience any force of attraction, and they have quite a high energy. And when they are moving into that direction, they simply leave the surface. We call them vapors. The process is then known as evaporation. And remember, if we have a closed container, this line is pretty important. The evaporation and condensation can both occur at the same time. By that, they mean, let's consider a closed container. If a few particles are going out, a particle may move back into the liquid surface, which means it's condensing. A particle moving out is evaporation. This one is evaporation. And a particle moving back is actually condensation.
Yeah, okay.
Okay. Now, although they do not discuss the, just a second, let me look it up. If that's discussed on the next page, that's fine. If not, we're going to discuss it here. Okay. One thing that is missing here in the book, but has been considered in past papers, is the factors that can affect evaporation. Now, before I get to sublimation, factors affecting evaporation. I'm noting them down here so that you may note them up in your book, and that would make it easy for you. Now, they usually don't discuss the factors affecting evaporation in your book because they consider it to be a part of prerequisite. They consider it that the students might have discussed them in their previous classes or grades. So the first factor that affects evaporation is pretty clear. That's temperature. We know higher the temperature, faster would be the rate of evaporation. However, there are some other factors too. For example, the nature of liquid is very important. Some liquids evaporate faster than others. We know the petrol, the gasoline.
Yeah, if the liquid is pure or not.
Right, right.
Yeah.
So the ones that have lower boiling point actually evaporate faster than the others, or the ones having higher boiling point. Now, apart from nature of liquid, we can also count wind speed or air speed as a part of factors. Higher the wind speed, faster the air is flowing around the area, faster would be the rate of evaporation. It's pretty easy to judge and guess that the clothes dry up quickly when we have some wind around the area. And when we don't have those windy days, the clothes won't dry up quickly. This can be consulted when you're going for some kind of heavy sports or for a workout. Now, the next up would be humidity. Not all the days around the year are similar, and not all the regions around the world are similar. Sometimes we have more water vapors in the area or in the atmosphere. We call it a humid atmosphere. Now, humid means it contains a lot of water vapors already. This would slow down the rate of evaporation. Higher the rate of humidity, slower would be the rate of evaporation because there are too many vapors of water already in the atmosphere. So you trying to dry up clothes or something like that, or water puddles would take time to dry up. All right. So these are a few factors that affect the evaporation and are considered in past papers as well, but are not given in the book. If you're done writing, I can erase them up.
Yeah,
and
I
move
took
forward.
all the notes. Yeah.
Okay, good. Let's move on. The next one we have is sublimation. Sublimation is actually a conversion of solid directly into a gas. This doesn't apply to every substance on the planet. This actually applies to very few substances. They convert from solid directly into gas, and from gas directly into solid, and they bypass the liquid state every time. This is sublimation, and the reverse process is actually deposition. And we are going to quote a few examples of few substances that can do that. Iodine is first on the list. Iodine can do that. CO2 or carbon dioxide can do that. Another
Am I
example.
required to know the specific compounds and
A few
elements that
right.
allowed?
A few compounds are discussed at this level. So those 2-3 names are important for you to know. So you're also supposed to memorize them because these are the ones you're going to experience whenever you're going to talk about sublimation as a process. And the last one is ammonium chloride. So there are actually 3.
So these are the only 4 that can go through the process of sublimation?
No, these are the only ones that are included as an example in your course. There are many more than that, but these are the ones that are usually included in IGCSE examples. Okay. And another word for deposition is desublimation.
Can you explain to me? Can you explain what goes on in the particles during the process of sublimation?
Yeah, the change is pretty much the same as we studied back in melting or in boiling. Actually, both of the processes occur at the same time. So what we are actually doing is that we are taking particles all the way away from one another and creating more and more distances in between them. So actually what we are doing is that we are using the heat to break up the attractive forces between these particles so that they can move freely and far apart from one another. So that's what happens.
So
when
in between the process, it turns into a liquid in between, yeah?
No, it doesn't turn into a liquid.
So it goes straight from solid to gas.
Yeah, that's why we use the word sublimation.
Okay.
All right. So this goes for iodine. If you look up iodine, and that's actually a part of your book, so let me explain. Iodine is actually a solid at room temperature. And when we discuss iodine as a solid, it has a gray-black color. Black is the easiest word to represent it with. But as soon as we start heating it up, let's say we heat it up, this black color would be converted into a gas, and the gas actually has purple vapors. So this change can easily be seen in lab. You can take a few small pellets of iodine, you can start heating them up, and quickly those gray-black pellets would be converted into purple vapors. Okay. Another example that we are usually commonly familiar with is carbon dioxide. Carbon dioxide is actually a gas at room temperature, and it's actually colorless. Now, we are familiar with this gas, but when we cool it up, it actually turns into a solid. And this solid has a specific name, which is, by the way, also given in your book, that is dry ice. It looks like ice. The only part is that it's not wet. We call it dry ice. Now, this dry ice is
Doesn't dry ice constantly emit like gas?
Come again, please.
Never mind.
Okay. So dry ice is actually used on stages for entertainment purposes. We usually have big machines in which we have pieces of dry ice. And whenever we give them electric shock, the heat is enough to convert them into gas. And we have that dense smoke effect on stages for the famous singers in concerts and other entertainment purposes like that. You might have experienced it or seen it, right? Have you experienced it at a concert where they have a smoke effect? Apart from the lightning and flickering effects, they also have the smoke effect. That smoke is actually produced from dry ice.
Yeah, that's what I said. Like I've seen a block of dry ice constantly emitting gas.
Right, right. And the gas is so dense, it appears as white smoke. Although carbon dioxide is colorless, but at that time it's so dense and it's coming from such a low temperature that it appears as white smoke. So that's actually sublimation. Okay. Now, if that's clear, I'm going to clear it up and move forward.
What is the third element?
The third element is naphthalene. Naphthalene. It's pronounced naphthalene. And this is N-A-P-H. Oh, I'm sorry. That's P-H-T-H-A-L-E-N-E. Naphthalene. Naphthalene is commonly present in the form of small white balls, and we usually put them in the wash basins of our toilets. To clear up the water that is going down the drain as a waste. It has a very specific odor, but in the most parts of the world, this is not used anymore for the said purpose, being a little bit poisonous. However, you're going to deal with ammonium chloride as an example, and ammonium chloride is a substance that is commonly used in order to demonstrate sublimation to the students in labs. We're going to come forth with an example containing ammonium chloride as a separation technique in the upcoming chapters. Okay. Now, as I was saying, that deposition is opposite to sublimation, and sometimes it's also called as desublimation. It's not written over here, but it's written in the key points. The key points are usually very important, so do tend to give them a proper time when you're reading through the book. Okay, so I'm going to clear it up and move on to the next page. Okay.
Okay.
Let's just move on. Carbon dioxide example is given over here, and the mentioning of dry ice is also given over here. Now, working out the physical state of a substance at a particular temperature. This is a very important topic. This is how they use the melting or the boiling points as in questions in previous papers. So this one's important. Now, a substance is solid at any temperature below its melting point. And in between melting and boiling point, it's a liquid. And above the boiling point, it's a gas. So if you're given with two pieces of information, the melting point and the boiling point, you can find out its state of matter at any given temperature. All right, let me clear myself up by giving an example. Let's say we tell you that the melting point of water is 0 degrees centigrade, and we also tell you the boiling point of water is 100 degrees centigrade. And if I talk about water and I give you any temperature as a part of question, let's say I ask you what would be the state of water at minus 32 degrees centigrade. So it would be a solid at that temperature, right? So these two lines
lower than the melting point, so it wouldn't have turned into.
Right, right. So if it's below the melting point, it's solid. If it's in between melting and boiling point, by that I mean at 53 degrees centigrade, it would be a liquid. And at any temperature, like let's say 174 degrees centigrade, it would be a gas. So it's pretty easy if you know this simple principle in these two lines, and you will always be able to work out the physical state of a substance at any particular temperature.
Yeah.
Okay.
So are we required to know any like specific temperatures of any elements, or will they always give us the melting and boiling points?
Yeah, that's what happens in the question, that they give you three pieces of information: the melting and boiling point,
Okay.
as you said, and they will also mention that specific or particular temperature.
Yeah. Okay, then this is easy.
Yeah, it's easy if we have all three pieces of information. Okay. Let's square it up. There, I have discussed a couple of examples over here, but I think it's easy if you understand the first two lines.
Yeah.
And that you already did. Now, room temperature, this is something important. Room temperature is different in different places, but in science, we usually take any temperatures in between 20 and 25 degrees centigrade. So usually for hotter countries, it is considered as 25, and for colder ones, it is considered as 20. That's what room temperature usually means. All right, let's keep moving on. We have another important topic at the same page, diffusion. Now, diffusion is actually the random movement of particles. That can be gaseous particles or liquid particles. And by this random movement, they are able to move through an area and spread out until they are evenly spread in an area. That's how we define diffusion. And not just that, sometimes we also use some bigger, more important terms to define diffusion, such as I can easily say that diffusion is the random motion of particles or the spreading out of particles from a higher concentration region to a lower concentration region. And that can be explained by a simple example of a smelly gas in lab. As soon as you open up a bottle of a liquid that has a smelly gas or vapors with it, if you're standing closer to it, you will be able to smell it first. If somebody is standing farther, they will be able to smell it later. That's because of diffusion. The particles are spreading out due to the random motion. And if you're standing closer, you're able to smell it first because it has the high concentration over there. And if somebody is standing at some distance, as there is low concentration over there, so they are not able to smell it first. But as soon as they're evenly spread out, they're able to smell it too, which usually takes some time.
Yeah.
Okay.
I'm clear on diffusion. So we can like skip this topic about diffusion.
Good. Okay. All right. This example has been used in past papers. Do you understand this one properly?
What? This example?
Okay. Because this example at this part of book is very simply explained.
Yeah, I've seen this before. Yeah.
Okay. Do you understand why one of them travels faster and one of them slower?
Because the ring is closer to the other side.
No,
so I will explain.
Okay, let me explain. The reason over here is not properly given because they don't discuss the masses over here. But let me tell you, this is a lighter gas and this one is a heavier gas. How do we know it? The mass of nitrogen is actually 14. The mass of hydrogen is 1, but as there are 3 atoms, so 1 multiplied by 3, and the total would sum up to be 17 if we add them up, right? And in case of HCl, the mass of hydrogen is 1, and the mass of chlorine is 35.5. And if we add both numbers up, the answer comes out to be 36.5, which makes HCl a heavier gas and ammonia a lighter gas. So a lighter gas moves faster and covers more distance, and the heavier gas moves slower and covers less distance. This is not explained at this part of the book, but as soon as they discuss the masses, and I believe that happens in chapter number 6, you are supposed to be able to explain them on the terms of which gas is heavier and why, and which gas is lighter and why. All right.
Okay. So we can tell how heavy a gas is by its atomic number?
No, it's actually the mass number I'm considering.
Yeah, mass number I meant, yeah.
Yeah, yes, okay. And we can tell about any gas, whether it's going to be heavier or lighter by the mass numbers. All right. So if that's okay, let's move forward. Diffusion is also possible in liquids. A small solid can diffuse or mix up into a liquid because of diffusion. But as this is slower, so it takes more time than the gas. Right? Which brings us to our topic of dilution of colored solutions, which means whenever we're going to dilute a colored solution, it would take some time for the dilution to complete for the entire area. And in order to speed it up, we usually go by the stirring process. That's why we have stirrers in lab to stir them up to make sure that we can dilute a colored solution. For example, this example is pretty good to understand. Imagine if you dissolve 0.01 gram of potassium manganate 7 in 1 cubic centimeter of water to make a deep purple solution. Now, if we take a volume of 1 drop as 0.05 cubic centimeter, we can work out that there are 20 drops in 1 cubic centimeter, and each drop will contain this much of potassium manganate. Thus, this is very easy and simple mathematics. And we can always work with this kind of mathematics to come up with the answers of how much a substance is present in a specific solution. Although you're not going to do that, actually, they're just giving you an example. You're going to go with much easier processes than this one, right? Okay, let's move on. Solubility of solids. Now, solubility is actually to be understood first, or what solutions are, and then we're going to discuss how solubility of solids or gases work. So let's start with solution first. Whenever we dissolve a solid in a liquid, the substance that dissolves is solute, and liquid which dissolves it is the solvent, and the solution is the mixture that forms is the solution. I hope you're clear with that. They're only going to define a couple of types of solution here, but let me explain that you are supposed to understand all different types of solution, and there are actually 6 different types that you need to know, actually 7. First, you should be familiar with soluble solution. If a solid can be dissolved into a liquid, that's a soluble solution. For example, we can always mix salt in water or sugar in water. That would be soluble solution. In case if we are using sand, it would be an insoluble solution. You should be familiar with that too. Now, these are the examples that we usually discuss for solids and liquids. These are the specific examples when we are discussing a solid and liquid. But if we are using liquid, we don't use the word soluble and insoluble. Instead, we have a different term that is miscible and immiscible. So if 2 liquids can be mixed into one another, for example, we can mix water with soda, or we can mix milk with water, or we can mix alcohol into water. Those are actually miscible solutions because both are liquids and both can dissolve into one another. However, we'll use the term immiscible if we're talking about something that is not dissolvable or soluble in water or in any other liquid. For example, oil and water cannot be mixed into one another, so we use the term immiscible solution for those ones. And let's say petrol and water, diesel or water are not soluble with one another, so those are immiscible solutions. And lastly, we have 3 more types. The first one is also given over here, saturated solution. Saturated means the amount of solid that can be dissolved into a liquid, the maximum amount of actually solid that can be dissolved into a liquid as much as possible at a particular temperature has already been dissolved. That is a saturated solution. For example, if we have a glass of water, and let's say we can add a tablespoon of sugar into it, right? And we start dissolving it, we will be able to dissolve it. What if we add 2 spoons? We will be able to dissolve it. It would require a little bit of stirring more than the previous one. What if we go with 3 tablespoons of sugar? After a lot of stirring, after like 20 minutes, we would still be able to dissolve it. If we could try to go with the 4th spoon, you won't be able to dissolve it at the same temperature. So having 3 tablespoons dissolved in water, that is an example of saturated solution, which means as much solid as was possible to be dissolved into a liquid, we already dissolved that much. All right.
Yeah, okay.
And unsaturated is the term used for its exact opposite. Anything less than 3 tablespoons would be unsaturated. Let's say you try to dissolve 2 tablespoons of sugar in water. So that's unsaturated. Why? Because you can dissolve 1 more spoon. So anything lower than the maximum amount is actually unsaturated. So that can be a spoon or a spoon and a half or 2 spoons, or anything lesser than the maximum possible is unsaturated. However, we can even dissolve more than 3 spoons of sugar in water. How we can do that? If we increase the temperature of water. That is usually done in order to make desserts. In order to add more sugar into the same part of liquid, we usually heat it up and dissolve more. Let me tell you a quick fun fact over here that you can dissolve up to 7 tablespoons of sugar in 1 glass of water if you heat it up. Approximately at 80 or 90 degrees centigrade for water, you can actually dissolve 7 tablespoons. So that's supersaturated. In order to properly define it, supersaturated is actually the solution which contains more amount than the saturated one. Because saturated was able to take 3, and if we are able to dissolve more, then that's supersaturated, right?
Can you explain that part again?
Okay. 3 is the maximum at room temperature. Let's consider the room temperature. Okay. So we call the one with 3 tablespoons, that would be the saturated solution. Anything that is less than 3 would be unsaturated solution, right? And anything that is more than 3, let's say we tried to dissolve 4 tablespoons of sugar or 5 tablespoons of sugar, but that would happen at a higher temperature. Remember, that always happen at a higher temperature. So we dissolved it probably like at 60 degrees centigrade. We were able to dissolve 4 spoons. That would be supersaturated then. Supersaturated solutions are always higher than the room temperature. All right. And the supersaturated are the ones that can contain more solute than what we are possibly able to dissolve at saturated solutions. So they usually contain more solute in the saturated solutions. That's why they are defined this way. Supersaturated solution has more solute than the saturated solution at a higher temperature. And that's the easiest possible definition. Fair enough?
Okay, yeah, yes.
Okay, good. Now, first we're going to discuss measuring solubility, and then we'll come back to discussing the solubility of solids and how it is affected by different factors. So I'm going to clear all of this written portion up, and we're going to move forward down the page. Can I?
Yeah, okay.
Okay. All right. So the solubility, a proper definition of a solid in a solvent or a liquid at particular temperature, is actually the mass of solute in 100 grams of solvent at a specific temperature to form a saturated solution. So we are, as in science, we specify the stuff, so we are specifying it. We're specifying the solute would be measured according to its mass. The solvent is always supposed to be 100 grams. We're supposed to form a saturated solution and at a particular temperature. That's how we define solubility. All right. So whenever we're going to compare solubilities of 2 substances, you're automatically going to assume that this process has been completed for those substances. In other words, it's the maximum mass of solute that dissolves in 100 grams of the solvent at a particular temperature. For example, if we talk about the table salt, the salt we eat every day, common salt, sodium chloride that is, at 45 degrees centigrade or at room temperature, you can only dissolve about 36 grams per 100 grams of water. And that's the saturated solution for it. And you can actually go for a practical investigating the solubility of solid in water. That can be easily done at any specific temperature. Let's consider an example. In this specific procedure, they are going to measure the solubility of potassium nitrate and that at 40 degrees centigrade, the solvent is water. So we are going to weigh an evaporating basin. We're going to heat a boiling tube of water just above 40 degrees centigrade. We're going to add potassium nitrate to the water in the boiling tube and stir rapidly until no more of it would dissolve. And there is undissolved solid left over, which is going to make sure that we have formed the saturated solution. Now allow the solution to cool to exactly 40 degrees centigrade. Pour some of the solution into the evaporating basin. This is important that you only pour off solution and no solid. You do not have to pour off all the solution, only some of it. Now weigh the evaporating basin and its contents. Heat the evaporating basin and contents gently to evaporate all of the water. And when it looks as if all of the water has evaporated, weigh the evaporating basin and its content, heat the basin again and weigh them again. Do the process over and over again, like 3 to 4 times. This is to make sure that all the water has indeed evaporated. And this is commonly known as heating to constant mass. This process, doing step number 5, 6, 7, doing the steps 6, 7, 8, and 9 is actually the heating to constant mass. All right, and we are going to move forward in the same diagram. That's how we do it. Step 1 to 3, step 4, a little bit of that is taken out. Step 5, we pour it up and we wait, we again heat it, we again wait until it's a constant mass, until the value of mass does not change. The value of mass will not change when all the water has evaporated. All right. This actually gives us the confirmation that we are done evaporating the water. It is then when you can finish up this entire practical process and move towards your calculation. Now, what is the calculation? Now, there are 3 easy steps to make the calculation. The first of all, we make a table. The mass of evaporating basin empty is 25.72 grams. The mass of basin plus the solution was 58. And when we dried the solution with just crystals, it was 38. If you subtract 38 from the 25, you'll get the mass of crystals. And if you subtract these two, the last two, you get the mass of water. So we come to know that this much of solid is dissolved in this much of water. And we can easily take the ratio to make sure that how much would dissolve at 100. For example, 12.28 grams of solid is the maximum mass that dissolves in 20. So 20 multiplied by 5 would be 100 grams. And this also needs to be multiplied by 5, so it's 61.4. This can be easily done in the form of ratio as well. Let me give you the idea. This is the solid, this is the water. The water is 20. Let's take the ratio sign, and this is 12.28. This is a little bit faster than the words written over here. So if that's 100, you can put this one as x, and it's very easy to solve. X would be equal to 12.28 multiplied by 100 and divided by 20. So in simplifying, this can be easily multiplied by 5. The answer comes out to be 61.4. So 61.4 grams per 100 grams of water at 40 degrees centigrade is the solubility of potassium nitrate at this specific temperature. So we can find the formula of solubility easily by this method. Solubility, the units for that is grams of solid per 100 grams of solvent, mass of solute, mass of solvent into 100. I think it should be clear, but if you have any questions, go ahead, shoot the question.
Yeah, no, so it's clear now.
Okay, good, good. Now, what we do is that we tend to convert into graphs, and we call those graphs as solubility curves. Let's take a look at a couple of graphs. Now, the solubility curve is actually the solubility of solid, and it changes with temperature, which gives you the idea that temperature is the factor that can affect solubility of solids, and we plot it like this. Take a look, we have temperature on the x-axis, which increases from all the way from 0 to 100. And on y-axis, we have 0 to 250 solubility grams per 100 grams of water. Take a look that it slightly increases for KCl, However, the value substantially increases for potassium nitrate or KNO3, which means KNO3 can be dissolved much more in amount at a higher temperature as compared to KCl or potassium chloride, right? Now, you should be able to work with these graphs. For example, they can come up with any kind of questions. Let me quote a few over here. They can ask you the solubility at any specific temperature. For example, what if they ask you the solubility at 56 degrees centigrade for KNO3? So you should be able to work with this like this to find out the value. This is known as extrapolation in mathematics. So you should be good with extrapolation. I hope that you already are, right? Good. So not just that, they're asking a single value is pretty easy of a question. Asking a comparison, however, would be somewhat more challenging as per IGCSE rules. So a comparison would be like this. You will always be able to work with that. And there is one important line that is given at the end of the page, and most of the questions work with this line. As soon as we decrease the temperature of the system from a higher value to a lower value, the solution or the solute actually crystallizes out of the solution or precipitates out of the solution. The example is already given over here. Take a look. They're working with potassium nitrate and they're cooling it down from 90 degrees centigrade to 30 degrees centigrade. And they're quoting the value of 150 grams of potassium nitrate released from the solution. How can you work with that? Let's clear up a little bit of these lines so we can work it out. Now, at 90 degrees centigrade, we have somewhat approximately around 200. And at 30 degrees centigrade, we have somewhat around 50. So that's 200 minus 50, which means 150 grams of solid would be released from the solution and will settle down at the bottom of that beaker or whatever piece of apparatus we were using to work with. And we use the words that it crystallizes out of the solution or precipitates out of the solution or released from the solution if we go from a higher temperature to a lower temperature. This is one very common question in past papers. They tend to see or check how the student is able to work with the extrapolation and can find out the values. If that's okay, we can move forward to the next page. Okay, good. Just a second. Let's clear it up, all of it up, and move forward. They have also given an example, a few questions that you can work with. There is a graph given. I think these questions are going to be easy for you. However, I would like to explain one question over here. Actually, B part 2. Use the solubility curve to find out the maximum mass of potassium chloride that would dissolve in 50 grams of water at 40 degrees centigrade. Now, let me explain that the whole graph is drawn for 100 grams of water. So they're asking you to work with 50 grams of water and at 40 degrees centigrade. Now, at 40 degrees centigrade, they have already calculated it to be 40 grams. So actually 40 grams dissolve at 40 degrees centigrade in 100 grams of water. But what if they're asking for 50 grams? Now let's work with that. Now, from the graph, we can see that the solubility is 40 degrees centigrade is 40 grams per 100 grams of water. From this, we can deduce half as much, or 20 grams would dissolve in 50 grams. The numbers we have used here are quite simple. But if you were, for instance, asked to work out the maximum mass that would dissolve in 34.6 grams of water at 40 degrees centigrade, this is the equation you're going to use. Because in simpler numbers, you can always work with the numbers. But with decimal figures or difficult numbers, you need an equation or you need a strategy to work with. So it's pretty simple. This is the same formula of solubility that we rearranged in order to work out the maximum mass that dissolves, right? Because when solubility was here, the maximum mass was here. So the mass of water over the 100 grams of water and its solubility values, and the maximum mass that dissolves comes out to be at our right-hand side. So let me explain myself again when I'm saying that we are actually rearranging the previous formula. So we actually rearranged this formula, right? We took mass of solvent, maximum mass of solute, and we take this value over here and 100 over here in order to work out with this value. This is what we wanted. So rearranging this formula in different forms is something that is going to help you with different questions. So remember the formula and remember how to rearrange it in exams or whatever they ask. Because this question is working with maximum mass of solute. They may ask you about the maximum mass of solvent for a specific amount of solute. So you should be able to rearrange the formula in any form, whenever or whatever, as per the scenario question demands. I hope that's clear. If it isn't, I can write different forms of this equation. No, actually the formulas are usually not given in exams, so you are supposed to memorize these formulas and you should be capable of rearranging them on your own. The formulas are not given in exams. So it's actually both memorizing the original formula, and the understanding part requires you to rearrange them as per your question. Okay. Now, let's move forward, clear it up at the same time. That's why I specifically picked second part of this example so that you can understand what they're doing. And this is the mass of how much the mass would crystallize out if we decrease the temperature from a specific higher value to a lower value. So this is pretty easy. We are already done with it with my example. So I think that's about it. Next up are the questions. We're done with the chapter, I guess. Yeah, we're done with the first chapter. These are all questions. You can work with these questions.